Oh no.
No.
Alright, hello everyone. For our project we examined the potability of snow. So our guiding question to start, how does altitude and depth from the surface affect the potability of water derived from snow? And to answer this, we first came up with a hypothesis, which was as the altitude of the samples increase, the potability will increase as well. Also, snow found closer to the surface will be more potable than snow found deeper in the snowpack. So variables, independent variables, pretty much the location of the snow, that was altitude and depth, and we hiked up Borealis Ridge and Van Norden Meadow. We hiked up there one day and then down there another day, and just as a reference point, we are right there. And dependent variables, turbidity, which is pretty much the cloudiness of the water, and then conductivity, since water in its pure state is non-conductible, we use conductivity to measure the ionized particles like in the water, and then total dissolved substance, which is pretty much the number of particles in the water. And we were going to do pH, but our instruments were like giving us varying measurements, so we didn't feel comfortable enough to come to a solid conclusion with that.
Okay, so our first experiment procedure was measuring depth and potability in terms of depth. And the first step is we found a place kind of out there outside the lodge to sample, and we looked for an area that was like off the beaten trail so that we can get the freshest sample that wasn't contaminated as we could. And the first step in that was to actually take a sample from the surface. Our second step was to dig a 1 meter hole down underneath that site that we took a surface sample from. And then our third step in that was to, down that hole, measure a 1/4 meter down, and for every 1/4 meter, take a sample out of the wall of that hole. Our fourth step was to repeat that at another location, still around this area, and just repeat steps 1, 2, and 3, where we take a surface sample, we dig a 1 meter hole, and then each 1/4 meter down, we take another snow sample. And then our fifth step was to measure the conductivity and total dissolved substances of each of these samples. And so, just to describe what a sample would look like, is we would take like a ball of snow, or like more than a ball, put it in a plastic bag, bring those bags back here, wait for them to melt, and then once they melted, we took our measurements on the melted water, and in total for this experiment we had 10 total samples.
Alright, so as you can see here, some of our results. Why are the bags here? On the y-axis, you can see the conductivity measured in microsiemens per centimeter, and trust me, I was just as surprised as you are to figure out that's an actual measurement. And then on the x-axis, there is kind of the depth under the surface, and you can see both the blue and red points modeling the 2 different sites where we ran these tests. And in both cases, as you get deeper, the conductivity goes up, which is in accordance with our hypothesis, meaning that there's more of a presence of ionized particles. In this next graph, you can see it's very similar. It's total dissolved substances versus depth. And you can see on the y-axis the total dissolved substances in milligrams per liter. And again, on the x-axis, the depth under the surface. And the reason these graphs look so similar is because total dissolved substances can actually be mathematically derived from conductivity. The two are interrelated because obviously the dissolved substances are what makes the water conductive, which is why there's this relationship between the two.
So next we began our altitude experiment procedure. We did this over Tuesday morning and Wednesday morning. And we did this because we wanted to make sure that, we could have done it Tuesday morning, Tuesday afternoon. We wanted to collect samples that were similar, so we didn't want samples to be sitting under the sun and melt a little bit. Fortunately, there was some snow on Wednesday morning, so when we went out again on Wednesday morning, we had to dig a bit underneath the powder snow to get to the more compact snow that was more similar to the stuff we found on Tuesday morning. But so step 1 was find an elevated location on the altitudinal gradient, then hike to the top of it. This is us on a rock at the top of Boreal Ridge, which, next slide, is 2,315 meters from sea level. This is the ridge that was watching over us as we sort of did our cross-country skiing yesterday. It's right back there. We spent Tuesday morning climbing up, and once we got to the top, we could begin step 2, which was every 20 meters ascended, take a snow sample from the surface. So as we were going down, Aidan had his phone, he was checking the altitude, and we would go 20 meters down, starting at the surface, at the top, and we would take a sample off the surface. We basically fill a bag with it, mark the latitude and longitude, take a photo of the place. Then Wednesday morning we began step 3, which was find a location lower on the altitude gradient. Then hike down to it. You can see here we are in Van Norton Meadow. And if you hit, there we go. You can see one more back. The rock up there is actually Boreal Ridge where we were the day before. So next one. Van Norton Meadow is 2,040 meters above sea level. And once we got down here, we could begin step 4, which was similar to step 2. Every 20 meters ascended, take a snow sample from the surface. This time was a little bit different for us because we crossed over, road and train tracks to get down there. So we took a few places, we took 2 samples at the same altitude. That way we could get one close to the human contact and one a little bit farther where it's a little more untouched snow. But again, like I said before, because there was a new layer of snow, we could dig a few inches underneath to get samples that were more similar to the stuff we took on Tuesday. And finally, we had step 5, which was work with Vivian to measure pH, turbidity, conductivity, and total dissolved substance. So as Shannon mentioned, our pH wasn't really conclusive because our meters were a little bit wonky, but we used a calorimeter to measure turbidity, and then we used an electron sensor to find conductivity and the total dissolved substance. And Vivian has some of the results.
Yeah, well here, so looking into the results real quick, what you're looking at right now is turbidity versus altitude. And as we probably before mentioned, turbidity just basically means how cloudy the water is. So if you were to have some dirty contaminated water would have higher turbidity, more clean water would have a lower turbidity. And so we took all these points and we plotted them and we realized that there were quite a few outliers, and if we just visually ignore them for a second, there was actually somewhat of a clear trend line. So what we did then is we used a combination of GPS location and photographs to try to find a common thread between the outliers. And then so
we asked ourselves, like, why outliers? Like Aidan said, we used like photos like these that we took at every single location to kind of find a common factor that caused these outliers. So we actually found out something super interesting. So like the locations where the outlier samples were taken, they generally have more human impact, which is shown in like the train track, or we also took a sample, sample 21, which we'll talk about later, which is taken near the lodge. And also another factor is there's less trees. And then non-outlier locations, there's in general like more trees and less human impact. They're usually more isolated places. So we did some research, and one of the sources of error we found was super interesting. It's that albedo effect actually has a exponential relationship with turbidity, and the reason, according to that research paper that we found, the reason why is because of the amount of suspended sediments and also the amount of radiation and the sun's like angle and reflection that actually somehow alters the turbidity due to the basically dissolved substances or sediments that are within the water that we collected. So yeah, we ended up taking out the outliers, and as you can see, this is a trend that kind of follows our original hypotheses, which is that as altitude increases, turbidity decreases.
Yeah, so we also measured a couple other parametrics with the water samples we took, and one of these was altitude versus conductivity, like we did with the first test run. And in this case, although the points still effectively scattered around the same area, they are still very varied, and we never felt like the data was actually conclusive enough to make any scientific claims. And then of course, total dissolved substances, its result is very heavily correlated with conductivity, and therefore we can't make necessarily a claim about altitude versus total dissolved substances either.
So the other major source of error, as we talked about, was the human. 1 second, you didn't mess with your computer.
Okay,
Sorry. And so sample 21 we took kind of near the path that we all had to come up to get to the lodge. And so obviously, like, everybody that comes here has to walk on that. There's a ton of human impact there, right? And so we took one kind of a little bit away from the path, and and the conductivity of it was 9, the total dissolved substances of it was 5.5, and the turbidity of it was 138. Whereas when we took the sample much closer to the path, it had a conductivity of 12, total dissolved substances was 6.82, and a turbidity of 258. And so it's very clear that human impact has a drastic effect on how drinkable water actually is. And so in the end, because of these unaccounted factors, the albedo effect and the human impact, and the measuring devices that we had were not really being that helpful, we ended up with a lot of strange data. And that means that our findings are somewhat inconclusive. They did demonstrate kind of some relationship to our hypothesis, and it was what we predicted, but it wasn't exactly what we were expecting to see. But in survival situations, it still is probably the best bet to get drinking water from snow at the surface, near trees, and at the highest altitude possible. And, if you're thinking about it, when you're in the wilderness, if there's human impact, why would you need to make water out of snow? Just go get it from where other humans are. So really, that actually eliminates one of the other major sources of error. And, I mean, last things last, the most important part of any scientific experiment, right, is reviewing the skills that we learned that can help us moving forward. And so we're going to go over the learning competencies that we have.
So the first one we use is critical thinking, because we have to plan ahead, right? We knew we would be hungry, and so when we packed our lunches, we had to make sure that they were big lunches, so that way we wouldn't be hungry later on in the day. We also have to be careful that when we put our feet in the snow, because if we put our feet in a dangerous spot, we would sink.
Second one is communication. Good to talk to.
We had to use creativity because originally we wanted to make snow cones, but then we realized we probably couldn't do that, so this was the closest we could get.
And resilience. You might think we're going to talk about hiking up the summit and all the way down to the meadow, but that was easy work. We used tests on 30 different samples using 5 different tests. We calibrated and retested 3 of these tests at least 3 times each, tried to test 5 different pH methods on all 30 samples, and then come to a conclusion that we won't even use the pH data.
And we
We all collaborated.
Thank you.
All right, does anyone have any questions for this group? Raise your hand.
I think we're gonna have to go with Daniel.
So I just want to lead off with this one and saying I think you guys did an awesome presentation. I thought you were really creative. I like all of your photos. You guys clearly like taking photos. It's very apparent from your presentation. But I wanted to say, like, you guys had, like, as you guys said with resilience, you guys did a lot of work, and it was a lot of hard work, and some of the data that you can even get to use. But at the end of the day, did you have fun?
I think I got this one. We really didn't have a fun time.
No, yeah, it was.
We had a blast.
Yeah.
How do you measure turbidity?
Turbidity is measured with the colorimeter, which essentially has a light sensor on the bottom of the clear, a digital light sensor on the bottom of like a clear pane that projects a set amount of light through it, and then measures the response.
I have a question. In terms of, so you measured water quality in a bunch of different places. Did you have a sense as to like where could you drink and where could you not drink? Like what's the, and like big picture, how polluted or not polluted was the water that you found?
So, like the general trend was that like higher altitude is better, but like this you kind of have to factor out. So like I would say in general, higher altitude, closer to trees, away from human impact, and closer to the surface of the snow. Yeah, that's like the general trend we found. But because our data, like there were some outliers, it's kind of inconclusive in some factors. So we can't like directly state that as a fact, but that would be our suggestion.
And there are things like in Boreal Ridge, I mean, it's the highest altitude that we went to, right? So you kind of expect it to be the cleanest, but what we actually found out is that the side that we went up was kind of the natural side, and on the other side there was a groomed side for a ski lodge nearby. And so this experiment, like, it wasn't removed from a lot of factors that did affect it. So it's needs to be kind of redone with more time because it took a lot of effort to actually go out and get the field data. And we just didn't have time to like keep going out to get more to do redundancy tests.
Yeah, I think the data shows that further investigation would be promising, but again, we can't make any conclusive.
Cool. And then just to contextualize it a little bit, the typical standard for TDS is 150 for drinking water. So like it can't be over 150 for drinking water. It's like one drinking water, whatever. Anyone else have any other questions? We have time for one or two more.
Real quickly, you don't have to go into a ton of detail. If you were going to do this over again, how would you do it?
I feel like one of the things that like we found was super interesting was that graph that we found from that research paper of the relationship between like albedo effect and turbidity. And if we knew that was one of the big factors, we probably would have like collected samples, like for example, like same altitude but closer to trees, away from trees, like that. Yeah, like that's kind of what we did with sample 21, but like we did that out of pure curiosity. It was kind of actually when we're walking up from the bus, like it's that road, and so basically we took one sample from where the cars are driving by and one sample from like closer to the tree, like where we can't actually like walk over, and like I think just being able to take different samples in the same altitude will probably help us factor out the errors.
Yeah, and building off what my group member said, I mean, Chris mentioned how difficult it was to collect data. I mean, if we had more materials and more time, we probably could have split it to two different groups and been able to collect a lot more samples that way in the same amount of time. And then, yeah.
All right. Nice work, everyone.